Hi, my name is Steven. So today I'm going to share our experience with running Flink at a large scale at Netflix. We're going to discuss the challenges and the solutions. This is the agenda for today. I'll first give a quick introduction how we run Flink at Netflix. Then I will give you some background knowledge on Amazon S3 services because we use S3 as our checkpoint store. So it's important for us to understand some of the design choices from S3 and the implications of those choices on scaling and performance. The main part of the talk are split in two parts. First, we're going to discuss how do we scale stateless jobs in the context of the routing job for our Keystone data pipeline. Second part, I'm going to discuss how do we scale a large state job. By large state, I mean a single job with state as terabytes of data and with parallelism at a few hundred or a few thousands. We run Flink on our Titus container platform. It's developed in-house. It's not open source yet. So Titus is responsible for container execution, resource management, and job management. As you probably know, Flink runtime consists of two components. First one is job manager, which is a master. Second component are the task managers. They are the workers. Together, they form a Flink standalone cluster. We create one title job for a job manager and one title job for task managers. We rely on titles for resource management. But here, for the purpose of isolation, we only submit a single job per Flink cluster. Flink state backend implements the data structure that holds the state. But in addition to that, it also needs to implement the logic to take a snapshot of the state and upload the snapshot to some checkpoint store. Usually, it's a distributed file system like HDFS or S3. We use S3 as our snapshot store because it is the only out-of-the-box support in Flink for Amazon Cloud. And it's a very good choice because S3 is very cost-effective and is highly scalable with a few caveats that we're going to talk about. And it's highly durable. I believe S3 claim their durability is 11 nines, so it's super durable. S3 is a massive storage system. Our data warehouse stores about 100 petabytes of highly compressed data on S3. An S3 bucket is a container for S3 object. An S3 object is identifiable by a key and a version if it is a multi-version object. S3 supports file system-like operations like get, delete, put, list. List basically is a prefix query on key names. And head. Head is a metadata request on S3 object. S3 shard data using range partition. Basically, S3 objects are stored in order across multiple partitions. With range partition, it's efficient for S3 to support prefix query. For example, if S3 only need to query, if you want to query an object with this particular date prefix, S3 knows it only need to look into partition 1 and 2. It does not look beyond that. But with range partition, it does bring some challenges for scaling. If the request rate grows steadily, S3 will automatically partition the buckets to support a higher request rate. The key word here is steadily. If you have big rollout, or if your traffic have a sudden jump, S3 may slow down or may throttle you. So if you use a sequential key names, for example, like a timestamp, S3 might target one specific partition for a large number of keys. That can overload the I/O throughput of that partition. So your transaction may be slowed down, or you may also be throttled. That's why S3 will recommend that you avoid sequential key names if your request rate is high, for example, over 100 requests per second. So they would recommend that you introduce some random prefix in the key names so that those objects can be spread to multiple partitions. That's how S3 can scale. Oh, I forgot to mention one thing. With random prefix, you do lose something because now you cannot do prefix query anymore because there's no prefix here. The prefix is just some random number. So you do lose something with the choice of a better scaling. So S3 is optimized for high I/O throughput. Means that you can stream gigabytes of data out of S3. That's not a problem at all. But it is not optimized for high request rate without tweaking the key names, like the random prefix I just talked about earlier. S3 is also not optimized for small files. Our data warehouse, they periodically compact those small files into larger ones. By larger file, I mean the file at the range of a few hundred megabytes. That can help improve the read throughput. S3 is also not optimized for consistent low latency. If you want to enable checkpoint every second in Flink, you may want to consider some other storage system like DynamoDB, which can give you the consistent low latency at the millisecond level. So you may not want to use S3. Now let's talk about how do we scale stateless job. Again, we're talking about this in the context of the routing job for our Keystone data pipeline. At a very high level, our Keystone data pipeline is responsible for moving data from producers to data sinks, where people can consume those data. Let's zoom in a little bit. Producers send the events to our founding Kafka cluster, either directly or via our proxy layer. Those data will land up in our founding Kafka cluster. Then our Flink router will pull those events from our founding Kafka cluster. Maybe apply filter and projection. Then deliver those events to data sinks. Right now we support 3 sinks: S3, Elasticsearch, and Kafka. Again, for this part of the talk, we're going to focus on the Flink router. At a very high level, our Flink router is very simple. It's a stateless job. There's no windowing. There's no aggregation. It's embedded in parallel, means that there's no data shuffling. So it supports like a source operator, maybe filter, projection, and sync. So it's probably the simplest Flink job you'll ever find. So the challenge here is the scale. Our Keystone router processes about 3 trillion events per day. They run on totally 2,000 routing jobs. And they run on 10,000 containers. Those 2,000 routing jobs, they have totally about 200,000 parallel operator instances. Let's do some math to see how many S3 writes we need to do for Flink checkpoint with such a scale. I mentioned that we have 2,000 routing jobs. If our checkpoint interval is 30 seconds, does that mean we're doing 67 S3 writes per second? Yes and no. Let me explain it. So if you look inside what Flink checkpoint does, as a checkpoint barrier flows through the job graph, each operator takes a snapshot of its own state and uploads the snapshot to S3. With that knowledge, let's do the math again. We have 200,000 operators. If each operator writes a checkpoint file to S3, with checkpoint interval at 30 seconds, then we're talking about over 6,000 S3 writes per second. Actual number will probably be 2 or 3 times smaller than this because for our routing job, only the Kafka source operator have state, and the state is very small. It's usually the Kafka partition offset. As I said, it's a stateless job. There's no other state involved. So even 2,000 or 3,000 S3 writes, it is still very high for S3. So not surprising we can get throttled by S3. Let's remind you that S3 is not optimized for high request rate without tweaking the key names. So initially, we set a Flink checkpoint path like this. We have a fixed prefix called checkpoints, followed by a deployment timestamp, then a unique job ID for each routing job. So this is the classic sequential key names that I showed you earlier because we use a timestamp. That's not very scale friendly for S3. So what we did is we introduced entropy in the checkpoint path. So before the deployment timestamp, we introduced a 4-character random hex prefix in the checkpoint path. Note that this does not require change in Flink. It is just a trick in our deployment tooling. Second thing for S3 is that it's not optimized for small files. So if we look in the checkpoint a little bit more, after the operator take a snapshot of the state, it will write the snapshot to S3. And the operator will send an acknowledgement back to job manager. In the acknowledgement, the metadata is attached. The metadata usually contains the location of the S3 file. After the job manager received the acknowledgement from all the operators, it will write a Uber checkpoint file to S3. This is how Flink achieves a globally consistent view for each checkpoint, even though each operator is taking the snapshot asynchronously at its own pace. So the problem now is that we have so many operators that are writing small S3 files. As we talked about earlier, that's not the ideal way for S3. It's not optimized for small files. Flink has this great feature called memory threshold. The default value is 1 kilobyte. Let me explain what this does. So when the operator takes a snapshot of the state, if the state size is smaller than this threshold, Flink operator will send the state in the part of the acknowledgement back to the job manager. So job manager will store the state first. After job manager gets all the acknowledgement from the other operators, it will then write the Uber checkpoint file with metadata and with the state embedded directly. So this way, operators do not write to S3 anymore. Only job manager write to S3 once. So we increase this memory threshold to a very large value, like 1 megabyte. This way, we avoid all the S3 writes from the operators on task managers. And only job manager write 1 Uber checkpoint file to S3. That's how we can achieve the S3 write like 67 S3 writes per second, because only 1 job manager write 1 file per job per checkpoint cycle. With this optimization, it also reduces checkpoint duration by 10 times, because S3 is not optimized for consistent low latency. If you're doing so many small S3 writes, obviously your checkpoint duration can blow up. The other strange thing we found with Flink is that on the S3 request is we found that S3 metadata request is about 100 times more than S3 writes. Why we are making so many metadata requests? So we first enable the access log on S3. First thing we found out is half of the metadata requests failed for non-exist objects. We are always making 2 metadata requests for the same object with and without the trading slash. This is because of the implementation from Hadoop S3 adapter. So, but we actually didn't pursue this problem because this just explains 2 times of the difference. We have because we're trying to find out what's 100 times difference. So we have a bigger fish to hunt here. After we fix the other big problem, this problem is tolerable to us, so we didn't even bother to pursue a fix on this problem. From the access log, if we just do some manual spot check, we find that those metadata requests, they mostly come from task managers. That's a little bit strange because we know task manager does not write to S3 anymore with the memory thresholds increase. So why we're still making so many metadata requests? So we use the BTrace, which is a dynamic tracing tool for Java. It can dynamic trace a running Java process by injecting tracing code. So this is the BTrace program we use. We first define 2 counters, one tracking the S3 writes, second counter tracking the S3 metadata request. To trace method call, you just define annotation. Here, in the bottom part, you can see we annotate to trace the Amazon S3 client class on the put object method call. If this method is entered, we increment the counter by 1. Second, we are define the annotation to trace the get object metadata request metadata method in the same Amazon S3 client class. And when this method entered, we increment the counter by 1, and we call jstack to dump the stack trace because we want to find out who is making those metadata requests, why we are making those metadata requests. So lastly, we define a timer of 30 seconds that's equal to our checkpoint interval. In the timer, we basically just dump the counters and reset the counter. To run BTrace is very simple. You just call BTrace with the process ID and the tracing program in Java that I just showed you earlier. So we run this BTrace on a 1 CPU task manager. It has 1 subtask and with 2 operators, source and sink. So it's very simple. Here are the findings from the BTrace. We confirm that there's no S3 writes from task manager anymore. So that's what we exactly hope out of the memory threshold. So that's working great. Second, we found that 4 metadata requests per checkpoint cycle. Remember, this task manager has 1 subtask and 2 operators, and each operator makes 2 metadata requests with and without trading slash. I don't expect you to read the full stack trace. I highlighted a few things here. Even though those Flink operators, task manager operator, does not write to S3 anymore, it still goes through the checkpoint code path. In that checkpoint code path, the checkpoint stream factory constructor is constructed every checkpoint cycle. And in the constructor, it calls the Hadoop file system make directory call, which eventually translates to metadata request for S3. So with that knowledge, let's do some math again on the metadata request. So we have about 200,000 operators. If each operator creates 2 metadata requests with and without the trading slash, and checkpoint interval is 30 seconds, then we're talking about 13,000 metadata requests from task managers, even though they write 0 S3 files for checkpointing. So that is a complete waste. Although metadata requests are pretty cheap, they still count as your request volume, so that when S3 enforce a quota or throttling, those are still counted. The problem is that we're creating this checkpoint stream factory every checkpoint cycle. If we only create this factory once during the operator initialization in the startup of the job, then we can avoid those 13,000 metadata requests. After we share the finding in Flink 1.2.0, Stefan Urban quickly fixed the issue in the 1.2.1. So I hope that you're running on a Flink version newer than this, then you should not run into the same problem that we experienced. The last thing I'm going to talk about scaling stateless job is a fine-grained recovery that comes from Flink 1.3. Let me first explain what is a fine-grained recovery. This is a very simple job. It has 3 operators, A, B, C. A could be a source operator. B could be a map operator, does some simple transformation. C could be a sink operator. This job has a parallelism of 3. Let's assume operator B2 failed. With fine-grained recovery, Flink will first try to find the upstream operators, which is A2. Then it will find all the downstream operators, which is A2, B2, and C2. This is the portion of the graph that Flink needs to restart for fine-grained recovery. Other parts of the job graph continue to run and process data. So why do we love about the fine-grained recovery? Let's look at the impact of a full job restart without the fine-grained recovery. In this graph, the x-axis is time. Y-axis shows the message per second. So here we're talking about the red line is input message rate to the Kafka topic. So the input message rate is about 800,000 messages per second, and is trending downwards. And the blue line is the message process rate from the Flink job. Ideally, those two should track identically. And in this experiment, we enable Chaos Monkey to kill 1 task manager every 10 minutes. You can see every task manager kill results in a full job restart, and subsequently a recovery spike of more than 2 times of the incoming message rate. So that caused a lot of duplicates. Although our application does not really require exact ones, excessive duplicate can still sometimes be problematic for them because it can skew their result beyond their tolerance level for duplicates. So you may wonder, why do you kill a task manager so frequently? Why do you kill every 10 minutes? This is actually to simulate a real-world situation. As I mentioned earlier, we run our Flink on our Titus container platform. When our Titus team push out new code, they create a new ASG. They want to evacuate containers from the old ASG to the new ASG. So what they like to do is kill the one container every Titus job every 5 or 10 minutes to evacuate those containers to the new code base. So this is exactly to simulate the impact of our Titus migration. After we enable the fine-grained recovery, this is what we get. First, if you look at the small bumps of those blue line, this is when fine-grained recovery is working. So the recovery spike is a subset of the job graph. So it's proportionally to the subset of the job graph that got restarted. But we also see full restart from time to time. Those are the big spikes are the full restart. So this is due to an implementation issue currently in Flink. So when Flink tries to perform the fine-grained recovery, if the replacement container did not come back in time, Flink will find there's not enough slots to schedule the fine-grained recovery. Then it will immediately revert back to a full restart in this case. Ideally, we would like Flink to retry the fine-grained recovery for some time before it gives up and revert to full restart. So we're expecting a fix as part of the flip 6. Our workaround right now is we add one +1 standby container to the cluster. This way, if one task manager gets terminated, we still have enough slots for Flink to schedule the fine-grained recovery. Obviously, if two task managers get terminated at the same time, we may still run the same issue and revert back to the full restart. But the likelihood of that is much smaller, and we are okay with that. With this +1 standby task manager, this is what we get from fine-grained recovery. Again, we are kill the task manager, one task manager every 10 minutes. This is a 20-node cluster. So every task manager kill is about 5% of the job graph. You can see the recovery spike is also about 5% of the incoming message rate. That is perfect. That is exactly what we hope out of fine-grained recovery. So it's working great. Let's recap what we talked about for scaling stateless jobs. We'll first introduce a random prefix in the checkpoint path so that we can spread the S3 writes from thousands of routing jobs to multiple S3 partitions. That's how we can scale the S3 writes. And also, we avoid the S3 writes from task managers by increasing the memory threshold setting. Third, we enable the fine-grained recovery with a +1 standby task manager to work around the current implementation issues in Flink. Now let's switch gears. Let's look at how do we scale large state job. By large state, I'm talking about a single job with state at terabytes, many terabytes of data, and a single job with parallelism in a few hundred or a few thousands. State of job often come with data shuffling, for example, using key by. So those kind of connected job graph, that brings some additional challenges in Flink in terms of failure recovery that we're going to talk about later. What we learned in scaling stateless job does not really help here, because here, a single job can write very large state, like terabytes of state to S3, from many operators inside the same job. We're talking about hundreds or thousands of operators inside the same job. And also, each task manager has a very large state to manage and to upload. Connected job graph that I talked about earlier makes fine-grained recovery. Fine-grained recovery cannot work with a connected job graph. Let's talk about those challenges one by one. First, a single job can write large state to S3. Because the problem here is the hundreds or thousands of operators from the single S3, a single Flink job is writing to S3, and because they share the same checkpoint prefix, and so this is also kind of like a sequential key name. That's not scalable for S3. So for this case, we have to change the Flink state backend code. We introduce this new config called the Inject entropy. So when this feature is enabled, we will dynamically substitute that underscore entropy underscore key with a random prefix during the initialization of the operators, so that each operator gets its own unique prefix in the checkpoint path. That's how we can scale the S3 writes from hundreds or thousands of operators in the same Flink job. So this does require change in the Flink code. After we enable this feature, we see a throughput improvement of over 2.5 times. We are working with the community to try to contribute this back. So if you're interested, you can follow on the Flink 9061. Second challenge for large state job is each task manager has large state, like many gigabytes of state. And so we have to tune Flink a little bit to stabilize our large state job. We first enabled incremental checkpoint on RocksDB. For any really large state, you probably want the RocksDB probably is the only state backend you want to use. And you probably want to enable incremental checkpoint because that helps reduce the checkpoint size and duration. Because you don't need to update the full snapshot anymore. Only the delta need to be uploaded to S3. And the Flink comes with great predefined tuning for RocksDB. So we just use the SSD predefined option for RocksDB. That works out great out of the box. We didn't have to spend too much time in tuning RocksDB. And because this large state job has parallelism, very high parallelism, like a few hundreds or a few thousands, so we need to increase the network buffer from default 1 gigabyte to 4 gigabytes. I'm going to show you some performance number, but we do not claim this is the best you can do with Flink. The goal here is trying to see what is possible with Flink right now and what is possible for us. I'm sure there's plenty of room of improvement, both in Flink and in our application. So I just want to give you an idea of what is possible. We do not claim this is the best you can do. For this task cluster, it has 200 task managers. Each task manager has 16 CPUs, 54 gigabytes of memory, and a little bit over 100 gigabytes of local disk. It has a parallelism of 3,200, which maps the number of CPU counts in the cluster. We first take a savepoint in Flink. For people who are not familiar with savepoint, it is like checkpoint. But the main difference is that savepoint allows you to rescale the job with a different parallelism. With checkpoint, you cannot rescale the job with a different parallelism. So after we take savepoint, we see the total state size about 21 terabytes. And it took about 27 minutes to take the savepoint. And when we recover a job from that savepoint, it took about 6 minutes. So when we enable the incremental checkpoint, the checkpoint interval is 15 minutes. And we see the incremental checkpoint size is less than 1 terabyte. So it's about 4 to 5% of the total state size. That is great. That's, I think, what the incremental checkpoint really helps here. And it took about 2.5 minutes to take the incremental checkpoint. We're pretty happy with those performance numbers. Obviously, as I said, there's a lot of improvement we can do, I think, both in the Flink in framework layer and in our application layer. But at least we know we're possible to a large state job as large as 20 terabytes. And it's possible and stable. So the last challenge I'm going to talk about for a large state job is the connect job graph. With the connect job graph, fine-grained recovery cannot work. For example, let's say B2 failed. Fine-grained recovery will try to find all the upstream operators, which is A1, A2, and A3. Then it finds all the downstream operators from that, which is essentially the whole graph. That's why with stateful job, with connect job graph, every failure pretty much results in a full jobs restart. What makes the job recovery even more expensive for stateful job is how Flink recovers data. Here, let's assume A1, operator A1, B1, C1 runs on task manager number 1, similar for operator A2 and A3. Let's assume task manager number 3 failed. The container gets terminated. So as we just discussed, that will result in a full job restart because of the connect job graph. With the job restart, full job restart, right now, all the operators on task managers, they go to S3 to download the data and recover those operators from data downloaded from S3. Is that really necessary? Because if you look at task manager number 3, yes, that container gets terminated, the data is lost, there's nothing you can recover. But if you look at task manager number 1, number 2, they're still up running, their local disk still there, potential data is still also there. If we can schedule the operators back to the same task manager, then Flink can potentially recover those operators from the data on their local disk. That is exactly what the task local recovery from Flink will do for us. I think that will come in, I believe it's coming in 1.5, if not maybe 1.6. So we're very excited about this feature. Because if you think about the last stage job I showed you in the performance number, if it's a 200 node cluster with 21 terabytes of state, instead all 200 task managers go to S3 to download those 21 terabytes of data. Now you only need one task manager go to S3 to download the 100 gigabytes of data. That makes a huge difference. That's why we're so excited about this task local recovery feature coming very soon. And task local recovery even works better with EBS. For people who are not familiar with EBS, it stands for Elastic Block Store from Amazon EC2. It is like a network attached disk. So it can be operated in a persistent, it can be a persistent EBS volume. So let's say EBS task manager number 3 get terminated. So the EBS volume will be detached. EBS volume will be detached. And when the replacement container comes back, it can reattach the same EBS volume. Then even for task manager number 3, it does not need to go to S3 to download data. It can also recover those operators from the data on the locally attached EBS volume. So nobody needs to go to S3 to download anything anymore for job recovery. Let's recap what they talk about for scaling large state job. We changed the Flink state backend to inject the dynamic prefix into the checkpoint path so that each operator in the same large state job have its own prefix, random prefix in the checkpoint path. That helps us to scale the S3 writes from the Flink job. Second, we enable the incremental checkpoint with RocksDB. That helps reduce checkpoint duration and size. Third challenge is the connect job graph makes the job recovery more expensive in Flink, but that's help coming soon, like task local recovery that we're super excited about. Yeah, that's all I get for today. So I'm open for any question, but if you're hungry, go get your food. I will be here, so yes. Yes. Yeah, that's for the memory. Yeah, that's for the memory threshold.
I'm wondering if you suffered a trade-off in fault tolerance when you did that because you were checkpointing.
No, it's not we're checkpoint less. We're talking about instead of the operators on task manager writing only those small checkpoint file. That state is shipped to job manager. Because job manager need to write that Uber checkpoint file anyway to give you the consistent global view of the checkpoint. So it's not to sacrifice anything for the checkpoint. Yes.
You are using a Uber checkpoint to, to write into one file, right? Is it this property specific to S3 backend, or can we apply for HDFS backend as well?
No, I think the Whoopok checkpoint is Flink for any state backend. Only any distributed file system like HDFS, they also need to write this Whoopok checkpoint file. No matter what the distributed file system use, HDFS or S3.
Okay. And the other thing is like you said the network buffer as 4 GB, and that is in the assumption that you are operating on 54 GB machine. Is that right?
No, I think the reason we need to increase is because the high parallelism in the job require us to increase the network buffer.
Okay. So that's just
but yes, obviously you need a more memory than this to make it work.
Yeah, because the higher version uses the percentage of for the network buffer. So since you said it, so we need the maximum. Okay, thanks.
Yes.
In case of stateless message routing setup, were you able to saturate network, and what should be like cluster size to saturate like 10 gigabits?
You talk about the routing job, right? Yes. So usually for a routing job, the bottleneck is in the network, as you suspected. So we do saturate the network for the routing job, and.
Did you have to do some tricks to saturate network, or was it just out of the box?
Out of the box, I think we can, because that routing job, as I said, is probably the simplest job you can ever find.
Yeah.
Does not do much, except for filter projection. Then it's very simple. Yeah.
Thank you.
Okay, it looks like we don't have any more questions currently. Thanks again, Stephen. That was an excellent talk.